Okay, exploring the solar system, part 2, spacecraft. Not explicitly to Mars, but spacecraft out into the solar system. So I'll be asking the question, how do we get there to the various planets? What do we do when we get there? Well, it's nice to take images of planets. And if we do take images of planets, how do we get the images back again? Of course, it's not just about images. We want scientific information about the various planets or moons that we explore. But most people, especially Joe Public, are interested in, if I can't see a photo, it hasn't really happened. So how do we get the images back again? And then again, I'll be asking the question, what happens next? When I started putting this talk together, I just wondered, well, how many spacecraft have we sent out into the solar system since we've been a spacefaring nation? And I started adding up all the spacecraft I could think of and very quickly ran out of fingers. And so I decided, well, I'm going to have to just Google it. And then I found how many spacecraft we have sent out there. And I know you can't read these, but it is literally hundreds. I think it's in the mid-200s, pushing towards 300. I've included this list up to the most recent one that I know about, Europa Clipper, which I'll be mentioning at the end of the talk. So there are an awful lot of spacecraft that have been launched, and some of which are still out there exploring the solar system. When it comes...
Just things that are in Earth orbit? Or are you saying beyond Earth orbit?
In principle, if they're exploring the Earth and the rest of the solar system, any part of the solar system, so they could be in Earth orbit, they could be at these parking positions called Lagrange points, they could be on their way out of the solar system. If it's a question of exploring Mars, this little cartoon is not to scale. If we want to get from Earth to Mars, that's one of the easiest planets to get to, because all we have to do is to fire a rocket when we're at Earth to put us on a slightly different orbit, not the green orbit, but the pale blue orbit. And if we give the rocket enough of a kick, it'll take us on this blue orbit and take us to Mars. So that blue orbit is an elliptical orbit around the Sun. At its closest to the Sun, it corresponds with the distance to the Earth. At its greatest distance from the Sun, it corresponds to the distance to Mars. So that's a relatively straightforward way of getting to Mars. The disadvantage is, given that it takes about a year for the Earth to go around the Sun and about 2 years for Mars to go around the Sun, this particular orbit takes about a year and a half. So in other words, it takes roughly 3/4 of a year to get from Earth to Mars. And it looks like if you decide when you get to Mars, I've changed my mind, I don't want to land, it looks like you just stay on that orbit and you come back to Earth again. Well, not quite, because it takes a year and a half to follow that blue orbit. So what has the Earth done in a year and a half? It's gone round the Sun once and half an orbit, which means the Earth isn't there anymore. The Earth is now on the other side of the Sun. So that's part of the catch. You can go to Mars, but if you come back again as quickly as possible, the Earth isn't where you want it to be. And you have to get the timing right of when you launch from Earth to Mars and when you launch from Mars to Earth. That's why a mission takes at least something like 2 years. And that's part of the problem with having a manned expedition to Mars. It was realized in the 1960s that you can get to other planets, especially the outer planets, by using a gravity assist. The purple here is the spacecraft. As it goes past Jupiter, you can get a slingshot or a gravity assist, which sends you off at much higher speed. And if you get the timing right, it can send you off in the direction of another planet. For instance, the Pioneer and Voyager spacecraft used this slingshot or gravity assist, and it would save you fuel because you don't need to fire a rocket engine. If you time it so that you go past Jupiter, you take pictures of Jupiter as you go past, but you use its gravity to send you on to Saturn. Or in the case of Voyager 2, it was using the gravity of Jupiter to send it on to Saturn, and then it used the gravity of Saturn to send it on to Uranus, and then it used the gravity of Uranus to send it on to Neptune. So you end up going much faster than you would otherwise, which is great because you get to explore the outer solar system more quickly. Still takes a few years, but you get to do it more quickly. And you don't need to fire a rocket engine, which means you don't need to take the fuel with you to fire the rocket engine, which means you have more payload for your scientific instruments or your cameras or whatever. So it's a great idea. It gets you there faster and you can take more scientific equipment with you. So this idea of a gravity assist is great, especially for exploring the outer solar system And it was realized in the 1960s that in the 1970s and 80s, the planets will be lined up in just the right way that you can send a gravity assist with minimum effort. And that's why the Pioneer and Voyager spacecraft were launched in the 1970s and then spent the next few years exploring the outer solar system. In terms of getting images back, here's a fairly early image. Any idea what it is?
Jupiter?
No, it's not Jupiter. If I tell you which spacecraft took the picture, then you'll know exactly what it is. This was taken by Luna 3. It's the far side of the moon, taken in 1959. So we can clean up the rather noisy image a little bit, but still you see, okay, there's a few splodges on there, but obviously it's not very high resolution. But this is the 1950s. This is before we had digital technology. So how do you get images back when you haven't got a digital camera to obtain the image electronically and then transmit it back to Earth? What they did with Luna 3 was take pictures with film emulsion. You remember film? Yeah, you remember that? Black and white image taken on film, and then on board, the film was then passed to a little chemistry laboratory, which then processed the film, developed it, fixed it, and dried it. Now you have effectively a negative. Then they used a cathode ray tube, effectively a flying spot, to scan the image, and a photomultiplier behind the negative would pick up how much light was being transmitted through this film, and that electronic signal from the photomultiplier was transmitted back to Earth. And then using that signal, they effectively reconstructed the image, much like a fax machine would take an electronic signal and then reconstruct an image from it. So quite a faff to do that, but the fact that it worked at all is amazing. The fact that it worked well is even more amazing. This is a much more recent image taken some 50 years later by Lunar Reconnaissance Orbiter, and there's a high-resolution image of the far side of the moon. It looks very different to the near side because we always see the near side from Earth and we can only see the far side from a spacecraft. But notice that the most recent images, all of the blobs are effectively in the right place. Dark areas, light areas are these seas, craters that we see similar to the near side. Basically, although it's low resolution, it basically got everything right. In the 1960s, that was replaced with digital technology. Mariners 4 and 5, flying past Mars, were the first to use a digital camera. Not only were they the first spacecraft to use digital technology, it was underneath the spacecraft there, the world's first digital camera. Digital cameras were built for spacecraft, and the spin-off is you now have one in your mobile phone. But they started as this is the way we're going to take pictures of the outer solar system because we are not going to use film and scan it and transmit it back. That's okay for the first try, but now we want to do things somewhat differently. So the world's first digital camera was placed underneath Mariner, and then you fly by Mars and you record everything that the camera sees on a continuous loop of tape, a bit like an 8-track. And they hoped that the loop of tape stopped in the right place. Otherwise, if it kept recording whatever the camera sees, as it flies past Mars and flies off into space, it would just end up recording black, 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 black. Luckily, it stopped in the right place. And after the flyby of Mars, they basically commanded it to go back through the tape and transmit what it had recorded, and that's how we got the first digital images of the surface of another planet. That was in the mid-1960s. Again, a little bit noisy, and again we can tidy it up a little bit, but we can see surface features, we can see craters, etc. And having this digital meant that although we can't necessarily transmit it back at the same time we're taking the images, we fly past in a few hours, and then we transmit the signal perhaps over a period of days thereafter to get the information back. We still have it in close to real time. Now, we've now explored quite a lot of the solar system. The solar system is 8 planets and a few dwarf planets and lots of other rocks and a few moons. We've now explored every major body in the solar system and some of the smaller ones as well. And again, I haven't got time to tell you about all of those, but let me just pick out a couple of missions to give you an idea of how it's worked. Back in 2004, a mission called Cassini went to visit Saturn. It was interested in Saturn, the planet, and the ring system around Saturn, and the various moons of Saturn, of which it has a lot. It was eventually crashed into Saturn in 2017. Why did they crash it rather than just sort of let it power down gracefully and just live out its life orbiting Saturn? Well, Saturn and Jupiter are unlikely to be places where life has evolved because the conditions simply aren't right. But there are moons of Saturn and moons of Jupiter in which we think the conditions for life do exist. In other words, there's water on moons, and if there's water and the right conditions, life might have evolved. And they did not want the Cassini spacecraft ever to crash by accident into one of these moons and possibly contaminate them. So they deliberately crashed it into Saturn, where it would safely die. To give you an idea of its size, in the bottom right there's a standard human standing next to Cassini. You can see these spacecraft are pretty large, and I'm not going to go through all the numbers, but there's some of the numbers that relate to the mission itself. Billions of miles traveled, hundreds of thousands of images taken and transmitted back to Earth via digital imagery, many gigabytes of data collected, and something like 360 engine burns. In other words, NASA instructed this spacecraft to change its position, change which direction it was going, change its orbit, or change where the cameras were looking to decide, I want to photograph the planet or the rings or the moons. So lots of interaction of telling it to move, telling it to take pictures, getting the information back again. So as seen from Earth, that's what the Hubble Space Telescope in Earth orbit sees of Saturn. But if we think about how much more information we can get if we, for instance, look at just the ring system, if we see what Cassini can see, because it's so much closer, it's able to see a huge amount of detail. The ring system is not a solid ring. It is thousands. It is millions, billions, trillions of tiny particles all independently going around Saturn, and so it's a very dynamic system, and trying to understand that system is one of the reasons that the Cassini spacecraft was there. It starts to look like a long praying record when you look at it from certain angles. It is a huge system. The ring system is 250,000 kilometers in diameter, but it's probably only a few meters thick. No more than a kilometer thick, despite being 250,000 kilometers in diameter. And when the sun hits the rings at the right angle, which it does every once in a while, they noticed, although most of the ring system appears to be relatively smooth, every once in a while they noticed the fact that some things were casting long shadows, indicating that some parts of the ring system are quite bumpy, and these bumps might be many kilometers or so in height. So again, trying to understand the dynamics of why is most of the ring system flat, but every once in a while you see bumpy bits of the ring system. The more you study these things, the more you understand. And one perspective that you can't get from Earth is, can you look at Saturn with the sun behind the planet? You can't do that from Earth. The sun is always over your shoulder because the Earth is one of the inner planets and Saturn is some distance away. But if you send a spacecraft to Saturn and fly into Saturn's shadow, then you see the sun shining through the ring system from behind, and the atmosphere as well. That's quite useful because the way light scatters off small bodies tells you about the size of the various small icy bodies that are in the ring system. And so they learnt quite a lot from looking at the way sunlight scatters through the rings when the sun is shining from behind. I said before that there's a lot of interest in Titan. This is the moon of Saturn that has a very dense atmosphere. I mentioned that one day we might send a helicopter there, but a stowaway, or at least an interloper here on Cassini, was this small spacecraft called Huygens, which was released to fly into the atmosphere of Titan. Titan has such a thick atmosphere that we can't actually see through it. And the question is, what does the surface of Titan look like? Well, until you send a spacecraft in, you don't know. So they sent in Huygens on a parachute, and as it came down towards the surface, it took these series of images. And so before this, all we knew was Titan is relatively large, larger than our own moon, for instance. But now we know that Titan is a world in its own right. It has mountains, it has lakes, it has rivers, it has clouds, It has rain, much like Manchester. But it's a world in its own right. We tend to think of moons perhaps as being very boring, but in fact this moon looks like it's very interesting. And understanding how this moon, the geology if you like, not quite the right word, but the geology of this planet affected its formation will tell us a lot about the rest of the solar system. So there are plans to return to this moon another day. Another example of a mission that's been sent out to the outer solar system is Juno, that's been exploring Jupiter. Again, loads of numbers there, huge amounts of data. In this particular case, 2 million commands sent and received in terms of, again, telling the spacecraft where it should be in terms of its orbit around Jupiter, whether it should be changing its orbit to go and visit this moon and take a picture of that, etc. So lots of interplay between the two. Again, billions of miles travelled, and in this particular case, terabytes of data received back from the spacecraft itself. If we look at Jupiter, let's just take Jupiter and unwrap it and remind ourselves that Jupiter has got these bands or belts, different colours. Why has it got different colours? Well, maybe the white areas, the white belts, the white bands, maybe those are ammonia ices. Why do we get these rather reddish, rusty colours? Perhaps that's other elements, sulfur or phosphorus, being dredged up from lower altitudes. We need more investigations to tell us what's going on there and why we get things like the Great Red Spot, this storm system that appears to have been raging for 400 years. It was seen 400 years ago and it's still there. Why do storm systems on Jupiter persist for centuries, whereas storm systems on Mars or Earth seem to dissipate after a short while? What's different about Jupiter that gives us storm systems like that? Juno's on a very elliptical orbit and it comes close to Jupiter every once in a while and takes a dive over the surface of the planet and produces images like this. Perhaps you notice the occasional white flash there. Those are lightning bolts in the upper atmosphere of Jupiter. So it's skimming over the top of the atmosphere, taking high-resolution images of these storm systems, and then over a period of a few hours, this is a time lapse, it'll pass Jupiter, and then on its elliptical orbit, eccentric orbit, it'll fly a distance away from Jupiter. Again, notice those white spots, storm systems that appear to be very persistent. It'll get a distance away from Jupiter, transmit its information back to Earth, and then it will take another dive close to the surface and see how much information it can pick up. These colours are exaggerated, but essentially true colours, but just exaggerated. So in other words, most of Jupiter is this sort of whitish or salmon pink colour, and the poles are bluer, not as blue as this would indicate, but certainly bluer. And again, understanding the storm systems are close to the pole is an interesting problem, especially if you think predicting the weather on Earth is tricky. What's it like trying to predict the weather on Jupiter? So we must remember that the solar system is not just the Sun and 8 planets. New Horizons, for instance, is a mission that was sent out to explore Pluto, a dwarf planet on the edge of the solar system, but it's now gone beyond Pluto and it's now exploring the icy belt beyond that, called the Kuiper Belt, and there are objects out there that we would like to understand. It's a rather difficult thing to do to try and steer New Horizons towards other objects. So what we're doing is trying to look at, are there any other objects in the direction that it's already travelling that might be worth photographing as it heads out of the solar system? And it's not just a question of planets and dwarf planets. There are over 300 moons in the solar system. I've mentioned some. Jupiter and Saturn have the lion's share of moons in the solar system. There's a few of them. Some of them are small enough to be potato-shaped. Some of them are large enough to be essentially spherical. There's Titan, where we can hardly see what's going on because its atmosphere is so thick. And some of them look more like the Death Star from Star Wars than they do actual moons. But if we look at the largest of the moons, these are essentially all spherical because they're large enough for gravity to make them spherical. There's again Titan with its very hazy atmosphere and we can't really see what's going on. There's our moon to scale. There's a lot of interest recently in the 4 moons of Jupiter. The one on the inside that looks like a pizza is Io. That's a volcanic moon, and that's interesting in its own right. But most recently, the interest has been on the next 3 moons, the so-called icy moons, Europa, Ganymede, and Callisto. These appear to be icy in the sense there's ice on the surface, but we have good reason to believe that below the surface there's water, liquid water. And there's probably more water on these moons than there is in all of the oceans on Earth. You take all of the Atlantic and the Pacific and every other ocean, add them together, there's more water on these moons than there is on Earth. So if there's water there and the right minerals and an energy source, then in principle life might have evolved on these moons. We can't see it by looking just at the ice on the surface. Again, we would have to think about how we're going to tell whether there's whether there's life in the water underneath the ice. So there are missions to go and explore the icy moons of Jupiter. The European Space Agency launched over a year ago now JUICE, the Jupiter Icy Moons mission, and NASA have sent their own mission called Europa Clipper, which is going to take a close look at Europa and probably the other moons as well. And they are both going to go into orbit and study these icy moons because they are so interesting because of the possibility of subsurface oceans and the possibility of life. How do we get all this information back from the other side of the solar system? Well, up till now we've been using radio. For instance, Cassini has got a big radio dish, and the radio signals will be sent from the spacecraft and picked up by an even bigger dish sitting on Earth. Huge, great things. But it's argued that there are better ways of getting information from different parts of the solar system. Instead of using radio waves, which we've been doing for the last 50 or 70 years or so, why not use lasers? Why not fire a laser back at Earth and have it picked up not by a radio dish, but being picked up by an optical telescope? So this was tested by a recent mission to one of the asteroids. It went to study the asteroid and it sent radio signals back. But as a test, they said, let's send a laser as well and see if we can fire a laser and have it picked up by this, the Hale telescope in California in America, with a 5-meter mirror. Relatively large, but by no means the world's largest telescope. Can we actually get this to work? So they sent a test. What did they send? There's no point in just sending an image. An image is far too small to actually test the data rates they were trying to get. So they decided to send a high-resolution video back to Earth on a laser beam. If you're going to send a video on a laser beam, what should the video be? They decided, well, it ought to be a cat chasing a laser beam. So they've got this high-resolution, high-definition video of a cat chasing a laser, and they transmitted it from different parts of the solar system. And they found that at a distance of 50 million kilometers, they could get a data rate of 260 megabits per second. That's faster than some people can get on their broadband when the server is 10 miles away. And this is from a distance of 50 million kilometers. Even when the spacecraft was significantly further away at 400,000 kilometers, sorry, 400 million kilometers, my apologies. At 400 million kilometers, which is way out there into the solar system, they still got a data rate of 8 megabits per second. Again, that's much faster than you need, for instance, to stream a Netflix video. So the idea that you can get data back really fast from the outer parts of the solar system, maybe radio ultimately is dead. It's going to be used for a few more missions yet, but maybe the long-term future is to use lasers to get information back in close to real time. So I've told you about Cassini, which is no more because it crashed into Saturn. Bepi Colombo is on its way to Mercury to understand more of that particular planet. New Horizons is on its way out of the solar system, and Juno is coming to the end of its life but is still up there looking at Jupiter. And I've told you that there are 2 new missions which have only just been launched, which are on their way, and it'll take a little while for them to get to Jupiter. The JUICE mission and the Europa Clipper mission from NASA. Again, a whole load of web pages here that tell you more. Don't worry about memorizing them. They're on the handout if anybody is interested. If your interest has been piqued, lots more information is out there about what has been happening and what will be happening in the near future. Thank you very much.